In this video, I'm going to show you how to use a protractor and a ruler to draw scale diagrams to add vectors together. In this first example, we'll have two vectors, both representing forces, a 5 Newton force and a 6 Newton force, labelled A and B respectively. And here I have a 30-degree angle between those two forces. So the first thing I'm going to do is choose my scale. You can see that I've got about 10 centimetres of vertical space, and I've got about 12 centimetres of horizontal space to draw my scale diagram. Now you may think that that means that I could fit in A vertically perhaps, where 2 centimetres is 1 Newton. That means A would be a length of 10 centimetres, and that would fit in that space. And B would be 12 centimetres, 2 times 6, and again that would fit in this space. But remember, I'm going to be adding these vectors together, and so I need a bit more space to make sure I can construct the diagram properly. So the scale I'm going to choose is 1 centimetre is 1 Newton. And I'm going to write that at the top here so I don't forget it. Next I'm going to draw my 5 Newton force. So very straightforward. I take my ruler, I put it somewhere in the top. I'm going to draw my diagram starting here and working down this way. So I'm going to start in the top here, and I'm going to draw my 5 Newton force 5 centimetres long. Draw an arrow on the end because it is a vector, so it has a direction, and label it 5 newtons, or I could have just labelled that A. And next I'm going to draw my 6 Newton force. But first I have to remember that it is 30 degrees around from the 5 newtons. And I could have gone in either direction, but I'm going to go down 30 degrees clockwise. So to measure 30 degrees, I need my protractor. I place my protractor so that the centre here is at the very beginning of the arrow, and that line of the protractor lines up with the arrow. And I'm going to read around 30 degrees, 10, 20, 30 degrees, and leave a spot. And now I know the line that connects from the beginning of the arrow through that spot will be 30 degrees to that 5 Newton arrow. So let's draw a 6 centimetre vector, so 6 newtons, starting from the beginning and passing through that dot. That looks pretty good to me. Draw my arrow and label it 6 newtons. And I could also label this angle here 30 degrees. Now the next step is going to be to add the 6 Newton force on the end of the 5 Newton force, and the 5 Newton force on the end of the 6 Newton force. I'll do both, and that will form a quadrilateral, which is a parallelogram. Now with a parallelogram, adjacent angles add up to 180 degrees. So that means the angle here will be 150 degrees, and the angle here will be 150 degrees. So as before, I'll take my protractor, I'll make sure the centre of the protractor is now at the end of the 5 Newton force, and I keep moving my head to place it over the top to reduce the parallax error in this measurement. And then I want a 150 degree angle, and you can see on the inner circle that that's there. So 150 degrees is in this direction. So I've placed my dot just as I did last time, and the line that connects from the end of this arrow to that dot is 150 degrees from this 5 Newton arrow. So I'll take my ruler and I'm going to draw a 6 Newton, therefore 6 centimetre line from the beginning of the arrow through the dot. Okay, that looks okay to me. Pen's running out a bit, but I think that's okay. And I'm going to draw an arrow on the end of that. And that is a copy of the 6 Newton force drawn on the end of the 5 Newton force. I can label this angle 150 degrees. I'm going to do the same thing drawing the 5 Newton force on the end of the 6 Newton force. So I take my protractor, I lay it down, Line it up, make sure the centre is in the middle, and that line goes through the middle there. And looking at the outer circle, 150 degrees is there, so I place a dot, and you can see it's really close to the other arrow. I take my ruler. A 5 Newton force will be 5 centimetres long, so I draw a 5 centimetre line in the direction of the dot, so from the beginning, sorry, the end of the 6 Newton arrow in the direction of the dot, so 5 centimetres long, and then draw my arrow. You'll see they don't quite meet, and that's because there's going to be small tolerances in my drawing. Don't know if you can see this on the camera, but I have a ruler with a resolution of 1 millimetre. Bit blurry, but 1 millimetre resolution means that all of my drawings can be plus or minus 1 millimetre at the beginning and plus or minus 1 millimetre at the end. There's some error in my drawing, but that's okay, that's normal. And I can just double check something. If I place a protractor on the end here, I would expect these two red arrows to be 30 degrees apart, and you can see they're about 29 degrees apart. And I've had to move the centre all the way over here to make that work. If I put it over here, then, well, I don't think I'm measuring the angle very accurately. So there's going to be some small variation in your answers, and that's okay. The examiner's expecting that, and there'll be a tolerance of what's allowed. So now's the important bit. The resultant vector starts here, ends down here, somewhere between the end of these two arrows. So I place my ruler like this, starting at the beginning, whoops, finishing down here at the end. That's the length of my resultant vector. And I'm just reading that number off now. It looks like it's 107, maybe 108 millimeters, or 10.8 centimeters, therefore 10.8 newtons. Well, forces are vectors, which means they have a direction as well. I've calculated, or I've measured from a scale diagram, what the resultant force magnitude is, but I also need to know the direction. And I could give the direction in two ways. I can either give the direction as an angle clockwise from the 5 Newton force, or as an angle anti-clockwise from the 6 Newton force. Now, if the 5 Newton force is horizontal, then I can say that this angle here is the angle clockwise from the horizontal. And how you present the angle doesn't really matter. The examiner's got a whole bunch of angles that they'll accept, as long as you say what you're measuring that angle from. How do you measure the angle? Use a protractor. So let's measure the angle clockwise from the 5 Newton force. I place my protractor just like this. You can see that the 5 Newton force lines up with 0. This blue arrow goes through 11 degrees. 16 degrees. I wasn't reading properly. 16 degrees. And that's to the nearest degree because the resolution of my protractor is plus or minus 1 degree. And I can do the same thing down here. Looking at the numbers, I really hope that equals 14 degrees. 16 plus 14 is 30. So I line the protractor up, just like that. The middle is at the start. 0 is along the 6 Newton force. And the blue arrow there is, yeah, that looks to me like it is 10, 14. That looks like that is 14. 1 degree shy of 15. And so there's my answer. I can give the direction in either of these two ways. Things to look out for. When you've drawn your initial diagram, there'll be a temptation to draw an arrow connecting from the end of one vector to the end of the other. We see this all the time. That's incorrect. Remember, you draw the second vector on the end of the first. On the end of the first, and it forms this quadrilateral, this parallelogram. and you connect from the start all the way to the end. So in this second example, we have two velocities, 15 meters per second and 7 meters per second, and the angle between those two velocities is 120 degrees. First thing we have to do is choose our scale. We need to get a feel for this, so have a look. 120 degrees is, if this is the 0 there, 120 degrees brings us down here, in this direction here. So I'm drawing on my protractor, down here. So we want to have a starting point somewhere probably on the top right and going down that way. Now, horizontally, I've got 12 centimeters. Vertically, I have got just about 10 centimeters. Now, given that scale, given the space I've got, I'm going to have to make a guess. If I get it wrong, I could always redraw it. But what I'm going to try is 2 meters per second is going to be 1 centimeter. That's the scale I'm going to try. So 2 meters per second is 1 centimeter, then 15 meters per second is going to be, look, centimeters is half the value, half the size of meters per second, so this is going to be 7.5 centimeters. I'm going to start somewhere over here on the right and have 7.5 like that. There's my arrow, and there's my C. 15 meters per second. And I've started from here. Now, just as before, I need to get my protractor to measure 120 degrees. Just like before, I place the center in the center, line it up, and leave a dot on the 120 degrees. It's an obtuse angle. Then I'm going to take my ruler, 7 meters per second. Remember that the meters per second is twice as big as the centimeters. So the centimeters is half as big as the meters per second. So 7 meters per second becomes 3.5 centimeters in the direction of the dot. Starting from here, going in the direction of the dot, 3.5 centimeters. And that's vector D, velocity D. I want to add those two together. Remember, the most common mistake students make is to try to connect here to here. That's nonsense. That's wrong. So what I need to do is to redraw, at 120 here, redraw D on the end of C and C on the end of D. Just as before, I know that adjacent angles in a parallelogram add up to 180 degrees. It's 120 plus, this must be 60 degrees here. And this must be 60 degrees down here. So I can take my protractor and I can measure that angle. Making sure my head is directly over the protractor to reduce any sort of parallax error. 60 degrees. There's my dot. And now I'm drawing vector D, 7 meters per second. Centimeters is half as many, so that's 3.5 centimeters in this direction here. And that's vector D, and this angle here is 60 degrees. And now I know the resultant is from the start to the end. Now I'm going to do the same thing. I'm going to draw C on the end of D. I'm going to take my protractor, line it up with D, end of the arrow's in the middle, 60 degrees, it's about here-ish, place my dot, take my ruler, C is 15 meters per second, centimeters is half the meters per second, so that's going to be 7.5 centimeters from the end of the arrow in the direction of the dot. That puts me to there. And you can see, just as before, the arrows don't quite line up. They should line up perfectly, but because of slight differences in my measurements, because of the tolerance of my ability to draw the diagram, somewhere between these two is the correct position of the resultant vector, the end of the resultant vector. And so we can either do from the start of C to the end of D, or from the start of D to the end of C. Doesn't matter, gives us the same line. which is that. Now I can measure that length. That's 6.6 centimetres. 6.6 centimetres, double it to get metres per second, is going to be 13.2 metres per second. And just as before, we'll better pop an arrow on the end of that because it's got a direction. And just as before, we can find the angle either anti-clockwise from C or clockwise from D. We can measure that using a protractor, just as we did before. Pop that on there. Okay, so I get 29 degrees. And I get let me line this up a bit better. Uh, 92 degrees. Okay. 92 degrees. Now you can see that 92 add 29 does not equal 120. So clearly somewhere around here my diagram was a little bit scruffy, about a degree out. That explains why the arrows didn't quite line up. But remember, there will be a small tolerance that's allowed. The better your diagram, the more accurate your diagram, the more likely it is you'll get the marks. But there are going to be small variations caused by the limitations of the instruments you're using. And that is how to draw scale diagrams to solve vector problems.